Advantages a connection machine has given to us is that we were able to speed these computations by a factor of 50 to 100.
I've been computing for 17 years now, and I've written many codes for vector computers that, in retrospect, were really just warm-up exercises to what we're doing today on these massively parallel computers like the CM5.
We have chosen the CM5 because we want to do a 3D simulation. The CM5 is a good computer to start with parallel computers because this machine is available with two programmation models, the data parallel and the message passing.
One of the things I've been most pleasantly surprised about with our CM5 is to see how quickly lots of different kinds of applications were able to take advantage of the speed on this machine. This is an updated version of my slide in which I keep each bar graph is a different application code, and this is the speed in gigaflops of that full code on our machine. Notice here that Schlumberger, an industrial company using seismic imaging, is going at over 50% the speed of the 512 machine. That's unbelievable. In fact, it's going faster than LinPack, something I thought couldn't be done on any machine.
The combination of higher performance and lower cost per answer has made it possible for scientists to do problems today on the CM5 that 5 years ago they couldn't dream of doing on any supercomputer. In particular, the fields of seismic processing and weather prediction are being transformed by this capability.
The work we are doing is also interesting for the oil industry. What we try to do is to use seismic data not only to obtain an image of the underground, but to compute parameters describing rocks.
Oil companies are very interested in understanding this in detail because it's through seismic prospecting that they can discover new oil reservoirs.
We're fortunate in the petroleum industry to have some applications that run very well on these machines today. We can get performances that are 50 times that of our Cray.
Another branch of research that I'm pursuing is to study earthquakes. It's my view that if we can simulate the physics of earthquakes in a sufficiently realistic manner on a computer, that then and only then will it be possible to understand whether or not earthquakes are predictable or controllable, and if so, how. The connection machine it's a beautiful system at the moment. It's well evolved, got software which allows me to develop on the massively parallel machine my codes easily. The languages are at a high level, and it's fast.
We have mostly students that when they arrived here, we already had the CM2, now we have the CM5, and they have never used a vector machine or a scalar machine. They have always been using parallel machines. And when they see other programs running in other machines, they are amazed of how strange they look like. So it's, from a programming point of view, it's wonderful.
Last year we showed on our Castle Day this weather application. And that went the following way. We used the CM5 for the calculation of the weather and the CM2 simultaneously for the visualization of the weather. And these two machines were connected by a Hippie switch. And I think this was a very nice application where both machines were used simultaneously.
We need one order of magnitude more power for this grand challenge problems like weather forecasts to see the details like thunderstorms and do visualization in real time, not interactively in 1 second, real time 20 frames a second. So we are looking forward to the next generation.
Now there's another mode of research which is prediction, which is much different than simulation, and that's where you try to actually forecast the movement and the direction of a storm in real time. So you're not really trying to understand what makes it work necessarily, you're trying to actually predict it based on the use of real data. So there's a clear distinction between simulation and prediction. So we're talking about bringing the scale down, bringing the time and space scale down, and having distributed numerical prediction centers that will provide very detailed forecasts, short-term forecasts that will have an enormous impact on things like aviation, agriculture, the insurance industry, power and electric utilities, gas utilities, the highway commissions when they're getting their road crews ready to go out. So the impact is really tremendous. And with the CM5 recently, we've made a high-resolution simulation 4 times the spatial resolution that had ever been used before in 3 dimensions. The one thing that has really been crucial for us is the development of the CMAX translation tool, because it represents, in my mind, the very first time where we're seeing a translation tool much like vector compilers were back in the 80s and late 70s, a tool that can be generally applicable to any type of Fortran code to make it run on a parallel machine.
The fields of material science and biochemistry have long been held back by a want of computing power. Industry needs to know how materials will behave based on their molecular structure, or how proteins will behave based on their chemical structure.
When massively parallel machines became commercially available, it was actually a relievement for me, and I just got a tool in order to express what I previously thought and just put on paper.
We are concerned here in our research with industry, in corporations with Daimler-Benz, for example, to simulate airflow around cars or combustion processes and visualize it. And we need massive parallel systems to have nice, very good results. Second application, especially here in Germany with the chemical industry, is molecular design, molecular dynamics, to visualize the results of the simulation process for new drugs, for the behavior of very huge protein molecules.
Recently, we've been working on protein folding, which is an attempt to determine the structure of a protein from the sequence of amino acids. From a practical point of view, this is something that would be enormously useful to drug companies. This is an extremely hard problem, and solving it would be a real revolution in molecular biology. But I think that the recent work we've done in folding myoglobin is really an advance in the state of the art, and one that would not have been possible without using our CM5.
Today we can comfortably run simulations with between 100 and 50 million atoms. And what's interesting about that size is that you start moving into areas that, or length scales that you can actually see in a microscope. So that's kind of the area that I'm using the CM5 for.
Engineers would always appreciate very much having information about how failure takes place and how to avoid it. And the phenomena that we are examining is always a precursor to catastrophic failure. Now, we always had theoretical understanding of it that didn't go far enough to the point that we give that to design engineers. Now, with the CM5 and with the new technologies, we were able to understand a lot more about how they evolve, and we are getting very close to providing engineers with actual information as to how to avoid it. That was never possible without the CM5.
We have carried out calculations on the CM5, and we've seen the transition from ductile to brittle fracture. There was the first time that transition had been modeled in 3 dimensions. We've done it before in 2 dimensions on a vector machine.
To design materials as well, to put in atoms in configurations that we have not ever thought of in nature, and then see if this kind of system is stable. Under what conditions is it stable? What are its properties? Does it have the properties that we'd really like to be to find in a material?
In the past, when we've modeled physical systems, the traditional way of doing it has been to have one code for each type of physical process being modeled. You might have one code for an electromagnetic simulation, one code for a fluid simulation, one code for mechanical stress. But real physical systems, real engineering applications involve all of these processes going on simultaneously. The power of the CM5 has made it possible for us to move from monophysics codes to multi-physics codes.
If you want to